Welcome to the video Spheroidal Graphite Cast Iron as a Material for Casting Part 2. Another very important issue is the segregation pattern. You see here you have a schematic nodule on the left, and on the right we have the grain boundary, that is the surface between two adjacent spheroids. Into this space, into this distance, we have the metal segregations. So you know the metal starts to freeze in proximity of the spheroid. That is an area that is called the first to freeze zone, and it is the metal freezes progressively up to the center between two adjacent spheroids in the grain boundary area, and the metal does not have the same concentration in all these points, but has a progressive decrease of the concentration for silicon, copper, and nickel that are said to be inversely segregating, and has an opposite shape of segregation with the lowest concentration near to the nodules and a high concentration at the grain boundary for manganese and moly. So this means that between the nodule and the grain boundary, from the first to freeze to the last to freeze, we have a continuous changing of chemistry that is very important for determining the subsequent reaction that we will have to manage during the cooling into the mold or by a treatment. So this segregation pattern is much more enhanced as the distance between two spheroids is large. So when we have a very high nodule count, nodules per square millimeter, so nodules that are a short distance, the difference between the first to freeze and the last to freeze concentration is low. And when increasing the casting thickness, the distance between two spheroids is increasing, this ratio between is making bigger from some elements or lower for the other element. And this is very important to be considered because it depends very much not only from the casting thickness and the nodule count, but also from the chemistry adopted and the technology inoculation processes and all the metal treatment that each foundry is using. And this makes very much the difference in quality, that is difference in mechanical properties, and it is different in machinability between one process and the other. In terms of absolute process procedures, but very much on the process scatters that we can experience into the different situations. So after the freezing, after the solidification, the metal cools. And during cooling, nothing happens at the spheroids, that remains as they are, but we have a transformation of the matrix. The transformation that you see on the red line means that the austenite is the carbon solubility into the austenite is decreasing, and the excess carbon is migrating to the spheroids and enlarging a little bit the spheroid diameter. And this happens up to the so-called eutectoidic temperature. This eutectoidic temperature is the temperature at which we experience the transformation of the austenite to ferrite and and perlite. So in this slide, next slide, we see how this cooling from the eutectic temperature to eutectoidic temperature into the mold is depending on the wall thickness. You see the horizontal time scale is logarithmic, and it depends on the casting thickness, and typically into the mold it takes the time of hours. When we arrive to the eutectoid temperature, the temperature stops until all the solid to solid reaction has been completed. And it is typically made by transforming austenite into ferrite at the vertical line on the left, or in perlite, that is the vertical line on the right, or a combination of both. It depends on the cooling rate, and it depends also on the chemistry that we alloying manganese and copper and other alloying elements that we have in the matrix. So we can get a fully ferritic structure if we have low manganese, no addition, and a sufficient slow cooling, or we can have a ferritic perlitic matrix where we have a spheroid that is surrounded by a ferrite shell, and then after this ferrite shell up to the last to freeze in the grain boundary, we have precipitation of perlite. Perlite is not a different structure. Perlite is a very thin structure made by ferrite and cementite, ferrite and carbide, in a very fine structure. So this is what we typically get in the cast condition. That it's for ferritic perlite is the so-called bull-like structure. Okay, where we have this ferrite shell surrounded by perlite.